Hello everyone, Mrs. Pasega here, and today we're looking at the Unit 8 Magnetism Review Guide for 5470. I know I say it every time, but it's because I want you to do this every time. Try all of these problems first. Then use this to go over the most difficult problems. You don't have to watch this whole video. Right? Now, something you should know about this particular review guide is each page matches up with one section of objectives. So the first page of the review guide goes along with section 1, and the second page goes along with electromagnets and all that good stuff. So another thing to point out, on the back side of this are all the direction rules. So with our magnetic field of a current carrying wire, the right-hand rule for electromagnets, and the right-hand rule for force. All of those are in the back page of this, and you can use them back and forth as a reference as you try these problems. Okay? So let's talk about permanent magnets. Permanent magnets have domains, and those domains come from the fact that their materials have these unpaired electrons. Material A can be made into a ferromagnet because it has unpaired electrons. Unpaired electrons have spins, and those spins don't cancel each other out for things like iron, nickel, and cobalt because of where they are in the periodic table. Something like material B, however, has all paired electrons. So like if this one is spin up and this one is spin down, they cancel each other off. So B has no net magnetic field. B cannot be a ferromagnet. Only things with unpaired electrons can be made into a ferromagnet. Now, let's say I get a bunch of material A together. Material A's atoms could form these crystals called domains. The domains of a permanent magnet will have not only the electrons line up, but also the domains line up. When the domains line up, they point in the direction of the North Pole. So in this case, my domains are pointing north. If I did the domains for this, domains pointing north would be to the left. In this case, domains pointing towards north would kind of go around this circle, pointing to the north. Domains are inside a magnet and they point north. That's one of the reasons, like in number C, why cutting a magnet in half results in 2 bar magnets or permanent magnets. If all my domains are pointing north, then I cut it into different pieces. Well, then right here becomes a south pole because domains are pointing away from it. Right here becomes a north pole because domains point towards it. So the magnet's polarity in each broken piece remains the same. Breaking a magnet in half makes 2 separate magnets. So outside, if we imagine our electrons are spinning, and the electron spins are what cause these domains, outside the magnets, you have a field. Field kind of makes a closed loop. So if domains point towards north, then field points from north to south. In this case, my field is pointing away from north towards south. For the horseshoe magnet, we should have more field near each of the poles, and the same for the bar magnet. So field points away from north and towards south, and this shape makes it be that there's more field lines near the poles. There's no particular equation to calculate magnetic field of a ferromagnet, but I do know that there's more field wherever there's more field lines. So in the following diagram, I can figure out my north and south poles because the poles are pointing away from north and towards south. Magnets cannot be monopoles, so if this is a south pole, then this is a north pole. If this is a north pole, this is a south pole. Magnets cannot be monopoles, and that's why when you cut this type of magnet in half, it makes 2 separate magnets. Cutting it smaller and smaller and smaller would still eventually leave aligned atoms and aligned electrons. But back to this problem. We labeled north and south. Then the greatest strength of magnetic field would be wherever there's the largest density of field lines. B is close to the pole, and it has a bunch of field lines running through it. And I bet if you counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, B has the greatest number of field lines. B is the greatest magnetic field. Now, I'm going to try and draw the same size box around A. It's not perfect, but we're kind of close. The same size box around C. The same size box around D. And if I count up the field lines, I would say C has 3 or 4 field lines, so C is strong. Then D with 2 field lines. Then A with the least. Field is strongest where there's the most field lines, and that tends to be near the poles. Now, permanent magnets are all well and good, but they're not as flexible as electromagnets. Electromagnets, the simplest or most basic electromagnet, is just when I have a current. So this current carrying wire is directed into the page. I can tell because there is a X symbol, and in this case the X symbol doesn't mean right, it means into the page. So the current in this wire is traveling into the page. A single current carrying wire makes the compasses line up in a circle. So I'm going to start by just drawing some circles for my field. But now I need to do the right-hand rule for direction. Please notice that I can just cross out into the page and out of the page. Those will not be choices. Know that the magnetic field around a single current carrying wire is a circle shape. Because it's a circle shape, that means my answers can be A or B. Now, how to do this is imagine I'm holding a wire, okay? And I need to point my thumb in the direction of current. So into the page means away from me. So I'm going to point my thumb into the page, away from me. And I don't know if you can see my hand here. Into the page, away from me, makes my fingers curl clockwise. So compasses would line up clockwise. I'm going to do the same type of rule for this one. No number here. This one. I know this is making the compasses line up in a circle. So as the current is going in a straight line, the field has to make a circle around this. To figure out the direction, I'm going to take an object, point my thumb in the direction of current, and my fingers curl around that object, and see how they're pointing down in front of the wire? Let's say I go draw that here. It's making a circle going around the wire. But I asked you to use the dot and X symbols. So here's a trick. Let's say I draw 4 little curls, and each of those represents like one of my fingers. Wherever the arrow is, whatever it's pointing to, is into the page. Whatever's on the other side then is out of the page because they're opposite directions from each other. That's how you can use the dot and X symbols. So one more time, I point my thumb in the direction of current. This makes my fingers wrap in front of the wire. On the bottom side, see how my fingers are going down towards the paper? That's into the page. And if I uncurl my hand, on the top side, my fingers are pointing out of the page towards you and me. So if the direction of current in the wire is reversed, the magnetic field stays the same magnitude, but switches to the opposite direction. For E, it's asking that point P is in the same distance R above our wire. So same distance R, but now the current in the wire is reversed. Ignore my drawing here. There's an arrow going to the left. That's what it would mean to be for the current reversed. If the current were reversed, then now my current would point left instead of right. I'd point my thumb to the left, and my fingers would wrap around in the direction of current. And it might help to like rotate my hand a little bit into an uncomfortable position. But that would mean my currents are making a circular field with X's above the line and dots below the line. Notice that if I rotate this problem, dots above, X's below, to this side, right? X's above, dots below, I get something that is symmetrical, right? I can just rotate one from the other. So if you can figure out one of these directions, then you actually can get any orientation of this picture. All right, in number F, it asks, what if point P is moved twice as far away and is above the wire? So let's say I move it out here. In the equation for a straight current carrying wire, the field depends on the strength of the current and how far you are away from it. That's why I had to use the special high current power supply, right? I needed a lot of current to make this obvious. And then I had to put the compasses really close. A compass that was far away from this field might not deflect and might not point in a circle because it's too far away. If it's twice as far away, I get half the field, less magnitude, same direction. Okay, so in G asks, what if point P is on the other side of the wire? What would happen to the field? Well, if it were moved to the other side of the wire, it would be the same magnitude, because think you're not changing the distance r. So let's say I put this here. Same magnitude, opposite direction. Because point P, if it was below the wire, would still be the same distance r away from the wire. So this is our distance r. So same size field, but opposite direction. I can double check that up here. If point P is on one side, a compass at point P would point down. But on the opposite side of the wire, it would still be pointing up with the same amount of strength. So same magnitude, opposite direction. And that leaves the last one on the page. What if the current in the wire is tripled? Well, that means a greater magnitude. If I had a higher voltage, higher current power supply, I'd get more field. It's just a nice direct relationship. So imagine for the current, if I put in 3 times as much current, I have 3 times as much field strength. Greater magnitude, but nothing else changed. So that means the current would point in the same, or the field would point in the same direction as before. This type of magnet is good because it's adjustable, but it's adjustable and very weak. I had to use large amounts of current to make that happen. So electromagnets are even better. Electromagnets with solenoids are even better because it takes the flexibility of adjustable current and therefore adjustable field, like the single wire, but wraps it around domains. And those domains temporarily line up so that you can make a core that turns on and off as you need. So how this rule works is that the North Pole is located in whichever direction your thumb points. So this time, notice your fingers wrap in the direction of current. And since the fingers are wrapping in the direction of current, I would take my object, wrap my fingers such that they're going up on the front of the object, right? Up on the front of the object. That points my thumb to the left. So north is at D. That must mean the South Pole is at B. That's what it means to not have monopoles, right? So if this is a North Pole, then the other has to be south. This is an example of a solenoid-shaped electromagnet because it uses electrical current to make that magnetic field. So let's say I'm doing a problem like C and D. That's going to repeat this. So what I want you to do is take an object, wrap your fingers in the direction of current. So in front of this pen, my fingers have to point down. So let's do that. In front of the pen, fingers point down. That puts my thumb to the right, making this a North Pole. And because it's not a monopole over here, it's the south. If I drew this out, maybe these are my fingers. And if it's my right hand, that's where my thumb goes. My thumb points north. All right, one last time. Let's say I take my object and I need my fingers to point up in front of that object. So I'm pointing my fingers up in front of the object. Thumb points left. That means this is a north, this is a south, and these would repel each other because south repels south. Opposites attract and likes repel. If I want to make this field stronger, I would want to change the current, the core, the coils, and the compression. With this equation, I can do some proportions. So quadrupling the number of turns would increase N 4 times bigger, making 4 times the field. But cutting the current in half would make there be less field. If something is quadrupled and then halved, I would get twice the amount of field that I did before. Now, to make the best field possible, I would want to use iron. Iron's relative permeability is high compared to even nickel and cobalt, which we know have domains and can become ferromagnetic also, but iron is orders of magnitude better. So it doesn't super matter that nickel is cheaper. Iron is the better magnet. So we want iron as the core to make the electromagnet stronger. Similar with G is talking about how both copper and iron could be used as a core since they're both metals. Copper is non-magnetic. Going back to the picture on the front page, copper is non-magnetic as its electron shells are filled for copper. It always has paired electrons. So copper cannot be a ferromagnet even if it is cheaper or both metals. Copper is not a ferromagnetic core, so that really wouldn't work. Now, we know that the planetary magnetic field has a lot of evidence for behind its origin, and probably one of the most important pieces of evidence is this seafloor spreading. Harry Hess discovered that as the seafloor spreads apart, this new magma is coming up here. Old magma hardens and gets pushed to the outside. So the strip representing the youngest seafloor is A. They're also symmetrical. So all of the rock in region A was formed together and cooled together. Since the North Pole at the time A was cooling down was in a certain location, all of these domains are going to line up pointing towards the South Pole of whenever that time was. The next strip, though, represents older rock. And during that older time period, the South Pole of the Earth was somewhere else. So the domains are opposite each other. The strips don't physically look like they're alternating. This isn't sediment settling down at the bottom of the ocean floor. This is different strips in the direction of the magnetic field. So if I had a compass that was like going over the seafloor, it would point north, then south, then north, then south, then north, and it would flip back and forth. This proves the magnetic field of the Earth changes. Right now, what we call the North Pole of the Earth, up here where like Santa lives, is actually a magnetic South Pole. Positive and negatives refer to charges, not poles, so it's never going to be positive, negative. Down here in Antarctica with the penguins, the geographic South Pole is a magnetic north. And that's why compasses point towards where Santa lives. They point towards Greenland and Iceland and Canada. Because compasses point south with field lines, that's where the magnetic South Pole of the Earth is. Another bit of evidence about the changing field of the Earth is that there's a lot of energy inside the Earth. We know there's a lot of heat because there's these tectonic plate movements and continental drift. Earth's tectonic plates move. And we know this because there's plant fossils, animal fossils, the Earth's overall magnetic field. We know that the Appalachian Mountains in the US match up with the Alps in Europe. Rock layers and mountain ridges on different continents actually match each other. As I mentioned, the seafloor spreading magnetic strips in the center of the mid-ocean ridge counts. The two that I left off here are the hominids and human language. To give you an order of magnitude, this was way before humans were around. If you remember this activity from class, we had like pieced together the continents, and this was like still dinosaur times, guys. We were not around then, and our early ancestors were not hominids at that point in time. We're like little squirrely mammals. So we were not hominids, and we definitely did not have language at that time. Ultimately, what causes this magnetic field of the Earth isn't the tectonic plate movement, but it's the idea, or the fact, that our Earth has a liquid layer. In the liquid layer in the outer core, that liquid layer has convection cells. So if you think hot rock rises, cool rock falls, we get these convection cells, similar to how we get weather up here on the surface. The hot magma is rising, the cool magma falls, and it makes these currents. As the metal brings electrons along with them, you get currents that add up, making the magnetic field of the Earth. We call this planetary dynamo theory, and any planet with a sufficiently thick gas, plasma, or liquid layer would be able to have this effect occur. It comes from the fact that the insides of all planets have heat that it has to disperse, so we get convection. It has to do with rotation, so things at the equator have to physically move faster than things at the poles, making a difference in pressure and making the fluid change directions. So Earth's magnetic field is caused by the liquid layer in the Earth. The solid layer on the inner core of the Earth is actually irrelevant. It's actually irrelevant because it's way too hot. The inside core of the Earth is, made of iron, but iron stops being ferromagnetic at about 500 degrees Celsius. Since this is thousands of degrees Celsius, the domains shake too much and they can't stay aligned. Now, this is really good because this magnetic field of the Earth extends way out away from the planet. And when it extends way out from the planet, that means that particles from the sun that interact with this field get deflected before they hit the surface where you and I live. Now, magnetic force acts on moving particles. That's why in the magnetic force equation, there's an ILB, I need the moving particles for current. If you look this up online, you might also see an equation for magnetic force with QVB. They're the same equation, but one is for single particles and one's for whole organized currents. I need single moving particles to have a force. That magnetic force doesn't significantly act against light. And ultraviolet radiation is a high energy form of light, so actually these two choices are the same choice. It's protecting us from solar wind. Solar wind is fast, charged particles. So solar wind is deflected by the magnetic field of the Earth because the field acts on fast, charged particles. Ta-da! So then we started getting into what do we use the force for? We take magnetic field and use it to make things like rail guns and speakers and motors. We tend to use it for things that can cause motion. So let's do magnetic force direction. This is another right-hand rule. And in this right-hand rule, current, field, and force all have to act mutually perpendicular to each other. So right now, the current is in the up direction, the Y direction. So my force cannot be up or down. My field is to the right. That's the X direction. So my force can't be right or left. That must mean the magnetic force is either into the page or out of the page by process of elimination. So I'm getting it down to two choices, and then I'm gonna right hand rule this. If it's comfortable, you can just rotate the page instead of rotating your hand. I'm gonna point my thumb in the direction of current and fingers in the direction of field. And how I remember which thing is which is I have several fingers, 4 fingers, and there's multiple field lines, but there's only one current, and I have only one thumb. So I'm gonna point my fingers in the direction of the field so that my field's pointing this way. My thumb is over here. And my palm is pushing in the direction of motion. My palm is pushing into the paper, away from me. So I would say this direction, into the page, away from me. B is about this direction thing too. So it asks, like, when will it actually make a force? It's not going to make a force if there's no current, so it can't be 3. A and B, like these two choices, are very similar to each other, and neither of them is correct. I mentioned they have to be mutually perpendicular, right? So if my current is going in the same direction of field, let's say my current is going to the right and my field is going to the right, the electrons in this wire aren't going to interact with the field lines, and therefore there won't be any force. Same as if it's going in the opposite direction. If you prefer a more mathematical answer, I need the current to travel perpendicularly to the field, because in reality, this force equation has a little bitty sine theta on the end. And if I put in sine 90 degrees, then I get a positive number for magnetic force. If I had them parallel, I'd put in sine 0, and the force would be 0. So in order to have a magnetic force, I have to have mutual perpendicularity. It has to be mutually perpendicular current and field. But now, let's say that I've got all that together. When you actually do the math for this, you don't actually need to use the sine theta thing. I just need to use ILB. The sine theta is there to help with directions. If I double the current, that doubles the force. Nice direct relationship. And flipping the direction of current just flips the direction of force. So let's cross off some. If the current in the wire is doubled, I should have a bigger force. So that crosses off 1 and crosses off 3. And if you don't know, you can strike through in formative. So if you find an answer that is not correct, you can click strike through and cross it off, and it will take that choice away and you won't see it anymore. That means I'm left with 2 and 4. The magnetic force will double in the opposite direction, because if you switch the direction of current, you switch the direction of force. And just for proof of concept, let's say I do the right-hand rule with this one. Right now my force is pointing into the page. If I flip the direction of current by flipping my thumb, now my force is pointing out of the page towards you. This force is often used for things like rail guns or motors. So what I need to do is draw the conventional current, and the conventional current goes from positive through negative up through this rod. So current is currently taking the up direction. So I'm just going to write this down so I've got it now. Current is up in the Y direction. The field back here with the X's is in the into the page direction, the Z direction. That means my force is either going to be left towards the power supply or right away from the power supply. Let's do part G and get the arrow for the direction of force. Now that I've got it down to 2 choices, I'm going to take my hand in my right hand roll position, my high 5 position. I'm going to point my thumb up parallel to the paper. My fingers are pointing down away from me. And that has my palm pushing to the left, which, not super ideal. I don't want this railgun, especially think like the Navy size railgun. I don't want this railgun to fire to the left. But that's where we're at. We've got the magnetic force acting to the left because the current, the field, and the force are mutually perpendicular to each other. Now, I need to do this secondary step of calculating the current. I need to do this because I can't calculate force without current. Current is the change in potential divided by resistance. That's Ohm's law. So with a 13-volt battery with a resistance of 6.5 ohms, that's a current of 2 amps. The magnetic force is I times L times B. So that's 2 amps times 0.4 meters times 0.5 field. And that gets me a magnetic force of 0.4 newtons left. Finally, let's calculate this thing's acceleration. Acceleration depends on an object's net force and its mass. Assuming no other forces in the x and y direction, my force would just be the magnetic force, so 0.4 newtons. The mass is 200 grams. That's not 200 kilograms. 200 kilograms is like 3 kids worth of mass. This is 200 grams. This is like the little tiny demo I had in class, all right? 200 grams is 0.2 kilograms. So please just double check for masses. Remember, kilograms is the base unit. Convert as needed by dividing by 1,000. 0.4 over 0.2 is 2 meters per second squared. In this unit, please know that I do expect you to remember Ohm's law. That was done many, many times in the last unit, and that acceleration depends on force over mass. Newton's second law. Very fundamental for physics, that are pushing things causes acceleration. In number 6, we know that moving electrons causes magnetic field. Induction is the opposite of that. If you have some sort of moving magnetic field, that should make electricity. That's what's up with this picture on the side. So the electrical energy in the coil comes from the kinetic energy you put in to move the magnet. In fact, if you do this, you can actually feel like a resisting force. There's a force pushing back against you that you have to overcome. So if the magnet is pulled quickly to the left, it makes a current, which makes like a voltage show up on the voltmeter. If I moved the magnet more slowly and to the right, it will produce less current because it's moving more slowly, less kinetic energy, less electricity. And switching the direction of motion will change the direction of current. So let's do this. Less current in opposite direction. That's I. If I had this as a north pole originally moving, how does it change the magnitude and direction? If I make more speed, it makes more energy. So it increases the magnitude of the voltage. There were no other changes in here, so it's still moving towards the coil. It's just going faster. So this is the same direction. If I move it slower and away, slower means you're putting less kinetic energy in, so you're going to get less current out. And the away instead of towards is going to mean opposite direction of current. When the North Pole magnet is stationary near the coil, there is no current, which I guess is technically a decrease. So a decrease from something to 0, that's a decrease. There's no current for this one, because if you have a stationary coil and a stationary magnet, neither thing has kinetic energy that you can use to translate into electricity. So no energy in, no energy out. If I switch from north to south, that's only going to change the direction. It's moving at the same speed, so I'm going to have the same current. So these two with the South Pole are going to have reverse directions, except this is two things. Think about this one. So I've switched the polarity from north to south, but also switched the direction. Oh, that's tricky. This will go in the same direction because it's like a double negative. So originally, let's say you switch from north to south, and that makes your current go whoop, opposite direction. but then you're making it go away from the coil instead of towards, so that switches again. Same direction. The faster speed means more kinetic energy, so more current. And fun fact, it actually doesn't matter which things move. In the videos for pivot, sometimes it was the coil moving and sometimes it was the magnet moving. So if it's the same speed and it's just the coil moving, so imagine this, this magnet stays still and maybe this comes by on like a cart with some wheels on it, it would still work. It would still give you the same amount of voltage and same amount of current. So a stationary magnet with a moving coil will still make the same magnitude of current. And it's the same direction because they were moving closer together before and they're still moving closer together now. Notice how I could answer a lot of these questions without doing math. I don't mean you to like pull out the flux and field and force equations for this. I want you to know that changing the speed and changing the field changes the voltage, in that reversing any one thing, so like reversing the field, reversing the current, changes the direction. So if I want to make the biggest current possible, I want the maximize voltage as possible. Remember, current from Ohm's law is the change in potential over resistance. So if I want the biggest current, I can either do more voltage, and there's many ways to do more voltage, or simply less resistance. I would take that as an answer too. If I make the same wire out of a better, less resistive material, that also makes that also makes more. So making less resistance would make more current, and maybe that means a material with a smaller resistivity, rho, from the previous unit. That might be something like changing from an iron wire to a silver or a copper wire. And more voltage has a lot of options. You can make stronger magnets, larger coils, because that makes a larger surface area that's exposed to the field, so more electrons move. You could bring the magnets and coil closer together, because that means a larger field will have more field lines going through the coil. I can make things go faster, because more kinetic energy in makes more electricity going out. If I wanted to use any of the equations for Faraday's law, I could say that the voltage was caused by more coils. So that N in that equation, more voltage, more coils, I could use that too. So lots of choices for this good short answer question. When the loop is not in the magnetic field, there is no magnetic flux. There's no field lines going through this, so the area is zero even though there is a field. Sometimes when it says determine, that's an indication you don't need to actually break out a calculator to get the answer. Because the area that's in the field is zero, the flux is zero. But where it says calculate, you probably do need a calculator. On the equation sheet, the equation for flux might have a little cos theta in there, but feel free to ignore it because I'm purposely giving you examples where theta is 0 degrees so that all the field lines are going directly perpendicularly through that coil. Okay, so you can just treat that as a 1. So when I do field times area, the field symbol is Tesla, so that's 5 Tesla is field. The coil has an area of 0.2 times 0.2, and that makes a flux of 0.2 Webers. Unless it says otherwise, feel free to assume that the number of coils is 1, n equals 1. So when it says calculate the induced voltage in the loop, I can assume n is 1. Because I'm given a speed in this equation, that kind of tips me off that I should be using the NBLV equation instead of the changing flux one. So if you were stuck from that, chances are you looked at these two and you're like, oh, I'm going to use the changing flux equation, but I gave you a speed instead of a time. So that's my indicator. I gave you a speed, you're probably going to use this. So I'm putting in 1 for n because you can assume it's one loop. I'm putting in 5 Tesla for B. That's my field. The length is referring to this length right here. But it's a square, so both of those lengths are the same number. So that's 0.2. And the speed is 5. This gives me a voltage of 5 volts. I did say before, and I'll say it again, I do expect you to be able to calculate current still. If the voltage is 5 volts and the resistance is 4 ohms, then the current is 0.8 amps. If I were to have 5 loops instead of 1, that would just be 5 times more voltage than 5. Right? So if I increase 5 volts times 5 loops, each loop gives me 5 volts, that's 25 volts total. Now the trick with this is as the coil becomes fully inside the field, let's say my coil goes to here. In the next moment in time, my field and area will not have changed. In the center, there's no delta V, there's no potential difference, there's no voltage, because while it's inside the field, there's no changing. So if I had to graph this out, when the coil is outside the field, it has a flux of 0. When the coil is entering the field, the flux is increasing. More and more of the area is getting bigger and bigger, so the flux gets bigger. But as it goes through the middle of the field, the flux stays the same. Exiting the field decreases flux, and it's only where flux is changing that voltage occurs. So I get voltage when you enter the field, voltage when you enter the field, but not while it's in the middle of the field. So where it says moving inside the magnet field, that's this line. This line is no voltage because the flux is not changing. That's why when I'm going to do G, the last problem on this page, C has no voltage because C is in the inside of this scenario. All 4 loops are like moving, but they actually have different lengths. A has a longer length than C or D or B. The length has to be perpendicular to the direction of motion. So if the direction of motion is to the right, the length for D is this shorter length. The length for A is the larger length. So A has the most voltage. B and D have the same voltage because they have the same length at the same speed with the same number of loops. B and D would just have simply different directions, because think of it like B, when it's entering the field, is going to get voltage in one way. D, exiting the field, is going to get voltage the other way. So, last page, all multiple choice, we got this. The electrical device that converts kinetic energy to electricity is a generator. A generator generates electricity. The electrical device that converts electricity to kinetic energy is a motor. A motor moves. M-O for motor, M-O for motion. All sorts of power plants use generators, and these are all going to be things with big spinning turbines, either running by like water spins the turbine. Actually, let's draw these out. So let's say I have my waterfall. The water spins the turbine, and as the turbine spins, it makes electricity. Nuclear, that's a fun one. Both nuclear and natural gas work by making things really, really hot. So I'm sorry that I can't draw. This is my fire down here. It then is going to heat some water up. This is both for nuclear and natural gas. The water makes steam, which is going to turn the turbine. And as the steam turns the turbine, then we get electricity. So hydroelectric, nuclear, and natural gas all use generators. Fuel cells are actually similar to batteries in that they're doing a chemical reaction. So it has no moving, turning parts. It's not kinetic to electrical. So the physics concept behind the electrical motor is that we have to create movement or motion. We're not creating voltage. So if we go back to number 5, in number 5, we are creating motion. And the thing we use for this is the magnetic force, ILB. It's not ferromagnetism, because that's what makes ferromagnets have a magnetic field. It's not electromagnets. That explains why like a nail can be used to pick up magnets with a coil of wire. It's not induction, which makes voltage, like all the Faraday's law bits are for voltage. It has to be magnetic force, because magnetic force is the thing that causes motion. This is the force that makes a railgun fire. This is the force that causes speakers to attract and repel. So as the current changes, the force changes and it shakes back and forth. A generator uses induction because it generates electricity, it generates a voltage. All right, everyone, best of luck.